Hello fans of GeoGebra, we have a new problem with a slight twist in the perturbation today. We have a frame pinned at the left end, roller at the right end, but the frame is an unusual shape. The angles, of course, are known, the positions are known, the loads are known. But let's find this right reaction here without statics. So the first step to do is to recognize that there will be a perturbation here, but rather than perturbing the right, let's perturb the point here that I'm going to call move me and redraw the frame starting at the pin, which doesn't move even in the perturbed situation, drawing a circle around the first leg of the frame to get the move me point, finding this angle between the original two legs here, which happen to be 149.04, and then establishing the second leg of the frame based on the radius, which would be this beam length. So the first radius is the first beam length, the second radius is the second beam length. And this angle is recreated here. So now I have this new point, which would be this point in the deformed situation. One more radius here would be the third leg of the frame based on this angle, which here it happened to be 153.43 degrees. So now I have this new dot here, and this is the new right end. This is the original right end, depending on the perturbation, which is now based on this point, move me. I'm just going to move this around and I'll show you. But what we need to do is get the actual perturbation for the right reaction, which is just the vertical distance between these 2 points. So just take the y component of this and subtract it from the y component of that, and that is my perturbation. One little maybe complexity here is that in the perturbed situation, we do need to establish where the loads are hitting the perturbed frame. That's really easy to do for the first one. I just drew a circle from the left pin through that load point lateral, and I found out where that circle intersected the distorted frame or the perturbed frame. Second step is just one little whisker different. There's probably another way of doing this, but I figured out how far the load point for the gravity is from this juncture, and I called that gravity load radius, and then from this juncture, the move me point, I made a circle of gravity load radius, and that was super easy. Now I can easily find the loft associated with each force. So the loft associated with the lateral load is obviously a lateral loft. The loft associated with the gravity load will be this vertical loft. So I'm just taking the vertical distance between the load point G and the horizontal distances between the load point laterals. And then the perturbation is, I already described that. So let's go to GeoGebra now and take a look at how this looks. So here you could see the lateral load deformation being negative for negative work. As I increase the perturbation, I'm moving from this point back to this point. So that's negative work because the load is going to the right, but the delta is going to the left. It's negative work for the gravity also. As I increase the perturbation, the gap is going the wrong way. So this is negative work. This is positive work for the reaction times its perturbation. So reaction times perturbation plus the negative work of the lateral plus the negative work of the gravity, all of that's equal to 0. And the reaction at the right is those two work energies, flipped signs, bring it over to the other side, divide by the perturbation. And look how fun this is. That even for this monstrous perturbation, I am really close to the correct answer theoretically here. And then the nice thing is we can keep track of the perturbation just by displaying it over here. And this is something that Mueller-Breslau could not have done. I can make that really, really small, really, really small. All right, let's just make it really small. And you could see the answer is crazy, crazy exact. It's asymptotically correct. As that approaches zero, these two match. But if you don't have the theoretical number in front of you, you don't need it. Just make this really, really small, and you got the answer for a frame.